In the last lecture, we discussed about the heat transfer in the various processes. I told you that for constant volume process, the heat transfer is given by mCv T2 minus T1. If it is constant pressure process, the value of heat transfer is given by mCp T2 minus T1. For constant temperature process, heat transfer is given by P1 V1 log natural V2 by V1. For reversible adiabatic process, the value of heat transfer is equal to 0, and if it is a polytropic process, in that particular case the value of heat transfer is given by mCn delta T, which is also equal to delta U into n minus 1 over n minus gamma. It is also equal to W1 to 2 into gamma minus 1 in denominator and gamma minus 1 in numerator, and the value of the Cn here is equal to Cv n minus 1 n minus gamma. This is how we can remember these relationships. Now I am proceeding to a numerical problem on work and heat transfer. So let us see what is the problem. A gas in a piston cylinder. When I say piston cylinder, it means it's a closed system. Undergoes an expansion. Whenever it is a expansion process, it means pressure is going down. That means the pressure is decreasing, for which the relationship between pressure and volume is given by PV raised to power n is equal to constant. So we are given with that the gas is undergoing a polytropic process. The initial pressure is 3 bar, P1 is 3 bar, initial volume V1 is equal to 0.1 meter cube, final volume V2 is equal to 0.2 meter cube, and we are asked to calculate the work for the process in kilojoules if the value of n is equal to 1.5, n is equal to 1, and n is equal to 0. So when I say n is equal to 1.5, we are talking about the polytropic process with n value as 1.5. When n is equal to 1, it means temperature is equal to constant. When n is equal to 0, it means pressure is equal to constant. So let us see how to calculate the value of work transfer in each of the cases. So first of all, we can write the data. It is PV raised to power n is equal to constant. This is the process. Pressure P1 3 bar, volume V1 0.1 meter cube, P2 0.2 meter cube, and for the case 1, the value of n 1.5, for B it is 1, for C it is equal to 0, and we are asked to calculate the value of W1 to 2. So once again same data. Now there are certain assumptions. So what are the assumptions? Let us consider the process is taking place quasi-statically. That means it's a very slow process. It is a reversible process. Only then we can use the relationship PDV for work transfer. Otherwise, we won't be able to use it. Secondly, the gas is the closed system. So we have a piston, we have a cylinder, but the gas we are considering only as the system, and piston and cylinder is not a part of the system. And for the process 1 to PV raised to power n is equal to constant, the work transfer is given by P1 V1 minus P2 V2 over n minus 1. Now for if you will see this particular equation, we know the value of P1, it is 3 bar. We know the value of P1, it is equal to 0.01 meter cube. We know the value of V2, which is equal to 0.02 meter cube, but the value of P2 is unknown. We know the value of n, which is given as 1.5 in case A. So that means we have to calculate the value of P2, then we will be able to calculate the value of the work transfer in this particular case. So we have the relationship P1 V1 raised to power n is equal to P2 V2 raised to power n. And from here we can calculate the value of P2. and P2 will be given by P1 V1 by V2 raised to power n. So P1 is 3 bar, volume V1 zero point 0.1, volume V2 zero point 2 raised to power 1.5, and we get this particular value of pressure which is 1.06 bar. This has been rounded to two decimal places. Okay, this has been rounded to two decimal places. So now we can put all the values here. P1 3 bar, V1 zero point 0.1, P2 1.06, V2 zero point 2, 1, and 1.5 minus 1. So we can calculate this value, but this will come in bar meter cube, and we have been asked to calculate this value in kilojoule. So let us see how to convert bar meter cube in kilojoules. So I have written it here. Bar into meter cube is equal to 10 raised to power 5 Newton per meter square. So Newton per meter stands for Pascal into meter cube. So it becomes 10 raised to power 5 Newton meter in, and this Newton meter is nothing but joule. So it means 10 raised to power 5 joules can be written as 10 raised to power 2 kilojoules. So it means 1 bar meter cube is equal to 100 kilojoule. Okay, so we have to multiply this value of work transfer by 10 raised to power 2 so that we get the value in kilojoules. So final answer for the work transfer for this particular case comes out to be plus 17.6 kilojoules. And you can see here I have written I have put a positive sign. What is the meaning of the positive sign? Positive sign shows that the work is done by the system. It means if this is the gas initially, then it is expanding up to this particular position, and the work is actually going out. So the work is done by the system on the surroundings because this value is positive. Now let us take the second case when the value of n is given as 1. When the n is equal to 1, it means the temperature is equal to constant. So if we will try to use this particular equation where W1 to 2 is equal to P1 V1 minus P2 V2 divided by n minus 1. And this is a valid equation for every process where the value of n is given. But in this particular case, the denominator will become 0. So rather than using this equation, we should use the basic principles, and using the basic principles we know that the value of work transfer is given by this particular equation for a constant temperature process. So once again I know the values of pressure P1, volume V1, V2 is also known to me, so I can easily calculate the value of the work transfer. Pressure is kept as 3 bar, volume is zero point 0.1 bar, multiplied by 10 raised to power 2 to convert bar meter cube into kilojoules, and then here we are putting the values of volumes, and finally the answer of the work transfer comes out to be 20.79 kilojoules. So this is how we can calculate the value of work transfer in case of a constant temperature process. Now we will go for a constant pressure process where the value of n is equal to 0. So this is the value n is equal to 0. It is a constant pressure process. So from the polytropic equation of the work transfer, what I can do is I can convert this value in work transfer in for the constant pressure process. So putting the value of n as 0, so I will get P2 V2 minus P1 V1, and I know because it is a constant pressure process, P can be taken out of the brackets, and I am left with V2 minus V1, and I know all these three values. The pressure is given as 3 bar, V2 is zero point 0.2, once again 3 into zero point 0.1, 10 raised to power 2 for converting bar meter cube in kilojoules, and final answer comes out to be 30 kilojoules. So this is how we can calculate the value of the work transfer. Now what we can do is we can add certain more portion to this numerical problem. We would like to calculate the heat transfer also. So I am considering the gas in the piston cylinder is air. So now I am considering that this gas is air and its initial temperature is 60 degrees Celsius. That means the value of T1 is equal to 60 degree Celsius. And we have to calculate change in internal energy and heat transfer. For each of these three cases, that means for n is equal to 1.5, n is equal to 1, and n is equal to 0. For all these three cases, we have to calculate the value of delta U, and we also have to calculate the value of heat transfer Q1 to 2. And one more thing which is given to us is the value of R for air is 0.287 and CV is equal to 0.718. And if we want to calculate the value of CP, then we know that Cp minus Cv is equal to R and Cp is equal to R plus Cv. So the value of Cp will come out to be 1.005 kilojoules per kg Kelvin. So that means this data is already given to me. So once again, now what I am considering, first of all, I am considering the value of n is equal to 1.5. That means I am considering the polytropic process. And in this case, while calculating the work transfer, we calculated the value of pressure as 1.06 bar. So I have made a table, so it will be easy for me to use these values. So pressure is 3 bar at state point 1, volume is 0.1, and the temperature is 333.15. It was 60, adding 273.15, I will get 333.15 Kelvin. So this is the value of temperature T1, whereas the temperature T2 is unknown. Pressure P2 is 1.06, volume V2 is 0.2. So this is known to me. So now I can calculate the value of T2 because W has already been calculated in the previous case. To calculate U2 minus U1, the formula is MCV T2 minus T1. So T2 is not available with me. Mass is also not available with me. So I have to calculate the value of mass and the value of T2. And after that only I would be able to calculate the value of U2 minus U1. So how to calculate the value of T2? I know that I can use this particular equation, which is TV raised to power n minus 1 is equal to constant. So I can use this equation. T1 V1 raised to power n minus 1 is equal to T2 V2 raised to power n minus 1. So from here, the value of T2 is equal to T1 V1 by V2 n minus 1. You can put the values here. After putting all the values, the value of temperature T2 comes out to be 235.57 Kelvin. See, this is one way of calculating the value of T2 or temperature at the state point 2. We could have also used the ideal gas equation or perfect gas equation, which is P1 V1 is equal to MR T1 and P2 V2 equal to MR T2. When we divide both these equations, MR and MR cancels out and we are left with P1 V1 upon P2 V2 is equal to T1 by T2. And from here, we can calculate the value of T2, which is equal to P2 V2 over P1 V1 into T1. And now you can put all the values of the pressures. P2 is 1.06, P1 is 3, P2 is 0.2, V1 is 0.1, temperature is 333.15. So this is the value of temperature T2. Previously, from the relationship when we calculated the value of T2, we got it as 235.57 Kelvin. So there is a minor difference between these two values, so it can be ignored. Now to calculate the heat transfer, what we have to do, we have to use this particular equation. But before that, we have to calculate the value of change in internal energy, which is given by mcv T2 minus T1. I have already told that the value of m is still missing. So once again, I can use PV is equal to MRT, this equation. And the value of m will be given by P1 V1 over RT1. So once again, we can put the values of pressure 3 into 10 raised to power 2, this much kilopascals, multiplied by V1, which is 0.1 meter cube, a value of R, value of temperature. So you can see it here. What I have done, I have written the units separately here and the values separately here. The value after calculating comes out to be 0.31376, and here you can see the units. For kilopascal, I have written it as kilo Newton per meter square. This is meter cube, meter cube. Kilojoule can be written as kilo Newton meter. then kg Kelvin, kg Kelvin, and Kelvin here. So this Kelvin and Kelvin cancels out. This kilonewton and this kilonewton cancels out. This is meter square and meter, so it becomes meter cube. This meter cube cancels out, and we are left with only kilogram. So this can be taken in numerator. So the value of mass comes out to be 0.31376 kgs. So now I can put the values of mass, CV, and delta T and calculate the value of U2 minus U1, which comes out to be minus 22.0143 kilojoules. And then I can calculate the value of heat transfer using this equation. This is the first law of thermodynamics for a process, and this is the value of the work transfer which we calculated in the previous example. This is the value of change in internal energy. So finally this is the value of Q1 to 2. If we have been asked to calculate the value of the heat transfer without calculating the change in internal energy, we could have, it would have been very easy for us, because we know that Q1 to 2 is given by MCV MCN uh, M into Cn into delta T. Delta T we have already calculated, and the value of Cn is equal to Cv upon n minus 1 into n minus gamma. So this is known to us. The value of n is known, gamma is known to us. Gamma for air is equal to Cp by Cv, and you can calculate its value as 1.005 divided by 0.718, and it comes out to be 1.4. So you can see it here. I have calculated the value of heat transfer using the work equation. This is the formula. Put all the values and you will get the value as minus 4.4. If you want to use change in internal energy, use this factor and calculate the value of heat transfer, which comes out to be minus 4.4. So if you see this particular value, there is minor difference. Okay, and this was the value which we calculated earlier. So basically, if you see, the first two digits are same in all the cases. So it's not a major mistake, and this could happen because we have rounded out the value of pressure initially when we were calculating the value of P2. Now we can calculate the value of change in heat transfer for n is equal to 1, that is constant temperature process. Once again, if I would like to calculate the value of U2 minus U1, this will be 0 because temperature is constant. So from first law of thermodynamics for a process, I can write delta Q is equal to delta W plus dU. This is the FLT for a process, and dU is equal to 0. So delta Q will be equal to delta W. And delta W we calculated, or W1 to 2 we have already calculated for the constant temperature process, and the value was equal to 20.79. So the value of heat transfer will also be same in case of a constant temperature process. Now let us take the last case when the pressure is constant. For a constant pressure process, this is the relationship between volume and temperature, that is V by T is constant, and I can write it for both the state points. V1 by T1 is equal to V2 by T2, and from here the value of T2 can be given as V2 by V1 into T1. To put the values of V2 by V1, zero point 0.2 by zero point 0.1 multiplied by 333.15, you will get the value of temperature T2 as 666.3 Kelvin. And then change in internal energy can be calculated. This is the universal formula for the change in internal energy, MCV delta T. So mass will remain same, which we calculated in case of the polytropic process, because it's a closed system. So the mass will not change, because the initial state, that is pressure, is P1, which is equal to 3 bar. Initial temperature is 60 degrees Celsius, and initial volume was 0.1 meter cube. Once the initial state is same in all the processes, the mass will remain constant for all the processes. So you can put the values of pressure, CV, this is T2, this is T1, and this is the value of U2 minus U1. Now to calculate the value of Q1 to 2, I can use this equation. This is the first law of thermodynamics. W we calculated for constant pressure process is 30, plus U2 minus U1 75.045. So the value comes out to be 105.045. Now here we have utilized the first law of thermodynamics. Had we been asked to calculate the heat transfer without calculating the change in internal energy, we would have used the equation Q is equal to mCp delta T, directly this equation. So you can see I have used it here. Cp I have already told you. So what you can do is you can put the value of mass, Cp and temperature difference, and you get the same value of the heat transfer Q1 to 2, which is 105.0417 kilojoules. Earlier the value was 105.045. So there is a minor difference in last two decimal places. So it's not a major difference. So this is what I wanted to teach you in today's class. Thank you.